Hello, my name is Andrea Villalobos, and I'm going to talk about the problem situation solution for the automation and control of chemical processes course. To begin with, I am going to talk about the motivation of the need for automatic control. Automatic control systems are on-site computerized system, sensors, and programs that can adjust and control of equipment and processes over the normal range of expected operating conditions without a manual operator assistance. This problem situation consists of a stir tank reactor, as seen on the screen, in which a second-order exothermic reaction takes place, as we can see right here. The reactant A gives us B as a product. Following the mass balance, the flow in equals the flow out. This means that the volume in the tank is constant. This tank also has a cooling jacket in its surroundings so that the temperature could be regulated. An automatic control is needed to control the concentration of the reactant A in the outflow of the tank and the temperature inside the tank. For this task, the next Simulink model will be used. Now talking about the equilibrium in the system. Equilibrium is a dynamic state where the concentration of reactants remains constant. This means that they may not be equal, but they are not changing throughout time. Considering that the reaction depends on the temperature and using the mass and energy balance of the system, we get the following model. After normalizing variables and using particular values for the parameters. This equation right here, the derivative of xt, will be used for modeling purposes of the system, and its equilibrium is given by these variables right here. It is important to note the result of these variables because they will be used later. For the equilibrium in the system, all input signals will be constant and have the following constant values seen right here. So now, for verifying the equilibrium, we use the Simulink model, but some modifications must be needed beforehand. The flow through the cooling jacket is inversely proportional to its temperature. Therefore, a negative response will be seen as the flow increases. Therefore, we make a change in the step input as seen right here. Continuing with the equilibrium, when we run the model, we can see that all the values previously calculated are indeed the same as the results of the scopes as seen on the next images. As I previously mentioned, the values of the variables are now seen in these plots. As we see on the graph on my left hand, the temperature xt is in 1.139 as previously expected. And from the graph on my right hand, we can see that the value of the reactant XA is 0.531. The concentration of reactant A decreases through time because as the reaction starts, it will be consumed to form the product B. The concentration should increase, but the graph decreases because of the change made on the zoom node. However, it will increase again since the speed of reaction is no longer being vaporized by the temperature. Finally, with the graph of the temperature at the cooling jacket, we can see that when it stabilizes, has a value of 0.926, arriving at an equilibrium point when the temperature at the tank is constant. Sorry, the temperature at the cooling jacket. Now explaining the design method used to find a controller for the system. For finding an appropriate controller for the model, first we need to calculate theta and tau to find them in the selected controller. As the equilibrium values showed, the temperature starts to 1.139 and the graph finishes to 1.164. So when we subtract those values, we get y of f, which is 0.025. Measuring the distance between the reference value and the step, the value for UF will be 0.2. With this information, we can then calculate K by using the following equation right here. K equals Y of F divided by U of F. Then we need the values for T1 and T2 by using these equations. We get the 28.3% of y of f, and we add the 1.139 where the plot starts, and we get the value of t1, which is 40.611. Then we calculate t2 by calculating the 63.2% of yf and adding the 1.139. Then we get that the value of t1, as we see right here on the plot, is 41.28. This is the value for t2. The value for t1 and t2 are seen on the cursor measurements shown in the lines right here. With these values, we can now calculate theta and tau by using the following second-order system of equations. When we solve this system, we get that theta is equal to 40.279 and tau is equal to 0.996. PID models feed control loop mechanisms employing feedback. This type of controllers varies in the way they correlate the controller input, ergo the error, to the controller output, actuating signal. PID controllers relate the error to the actuating signal in a proportional, integral, or derivative manner. One of the possible combinations is the PI control, which is a form of feedback control. It stops the system from fluctuating and is also able to return the system to its set point. PI control correlates the controller output to the error and the signal of the error. The P-only control is only in action when the system is not at the set point. When the system is at the set point, the error is equal to 0, and the first term drops out of the equation. The system is then being controlled by the I-only portion of the controller. Should the system derivative from the set point again, P-only controls will be enacted. With the following table, we can now calculate the appropriate values for the selected controller. As we are using a PI controller, we are calculating the Kc and the Ti constant for the system. P equals to Kc and I equals to Ti. And these are the values that we got. These values will be set in Simulink, and we get the following results. When we implement the controller in the simulation model, we get this scope. As it can be seen on the results on the previous scope, the PI controller do its job as the partial part is controlling the speed of the response in the beginning of the graph, and the integral part is eliminating the control error in a steady state. So now, for concluding, throughout this semestral course, I learned about the importance of the automation and control in chemical processes. Some of the most valuable knowledge I gained was about PID controllers and how they help in the control of variables in processes so it may be more efficient and safer. Thank you for your attention.